Okay, so we are doing sequences in series. We haven't gotten to series yet, but we're doing sequences. And what we talked about last time was just the basic definitions. So right, you have some sequence, like piece of n in a metric space. Right, piece of n, some metric space, and then we say that the sequence converges to a point P if something happens, right? Can anybody remind, maybe take 10 seconds and write down what the definition is, right? What does it mean for a sequence to converge to a point? You must have come from some odd angle. I just went outside and looked, and I saw nobody there, and then you've just appeared. Where did you come from?
I don't know. Over there, I was walking really fast.
Oh,
So
okay, yeah. Okay. Yeah. So does anybody remember what convergence to a point means? What does it mean for a sequence to converge? Hey, Charlotte.
The limit as n goes to infinity equals p.
Yeah. So what does that mean? What does that mean? Right. What does anybody know? What does that mean? So I mean, so that's sort of like saying that that's another way of saying it. But what does it mean precisely? Oh yeah.
For any neighborhood around P, we can find an n such that for any n greater than that, we're in the neighborhood.
That's right. That's right. So it means that you know, if you take any epsilon neighborhood of that point, right? If you take any epsilon neighborhood of that point, then you can find some time past which everybody's in that neighborhood, right? So given any neighborhood of P, there exists a time such that whenever you're past that time, then P sub n lies in that neighborhood, right? So you know, maybe one way you can say this is that you can make P sub n as close to P as you want, right? You can make P sub n as close to T as you want, right? And like, right, in such a way that you get they're not gonna leave that neighborhood. Okay. So yeah, so we did that, and then we did a bunch of basic facts about convergence. And then what we're going to do today is talk about sequences of complex numbers. Okay, so instead of an arbitrary metric space, we're going to have points that are complex numbers. Okay. So right, so we've got our complex plane, and we've got your time 0, 1, 0, 1, 2, 3, 4, right? And you've got some map from the natural numbers into the complex plane. Okay, so so the first thing, we'll talk about like how convergence interacts with arithmetic, right? Because the complex numbers is not just a metric space, but it's a field, right? So you've got you can add things, you can multiply things, you can divide and stuff like that. Right, so here's the theorem. So you have, suppose that you have two sequences, Sn, you have two convergent sequences, okay? Sn converges to S, and Tn converges to T in complex numbers. Okay. And we're basically gonna talk about how sums and addition, sums and products and stuff work. Okay, so first off, as you might expect, if you look at the sequence that you get from adding them together, well, what's that going to do? The sum of the sequences is going to converge to the sum of the limits, right? Right. Or another way of saying this is that the limit of the sum equals the sum of the limits, right? So equals the limit of the first guy plus the limit of the second guy. Right. So you can add and then take the limit, or you can take the limit and then add. Right, so those operations commute. Okay. The second one says that if you let, let's say you have a constant in C, and you multiply one sequence by it, then of course that's going to converge to the constant times the limit. Right. So again, this is a commutation comment, right? That the limit of the scaled sequence equals the scale of the limit, scaling of the limit. Third one, that if you take the product, it converges to the product of the limits. And the fourth one, that if you take the quotient, if you take the reciprocal of a sequence, then it converges to the reciprocal of the limit. So these are all things that you probably saw in calculus too, but I doubt that they were explained because you didn't have the notion of convergence. They couldn't explain it. Okay, right. Right, and right. So of course, if you have this sort of thing, then that gives you that the limit of a quotient is the quotient of the limits, right? Because you just if this goes to that, then T sub n over S sub n is going to go to, right? T sub n over S sub n is T sub n times 1 over S sub n, right? Which by the previous one is going to go to T times 1 over S. So we don't need to do this. We just need to do reciprocals. Okay. Okay. So let's do these. The first one. So let's think. I think you can probably do the first one. Okay. So think. So assume that. Assume that S sub n goes to S, T sub n goes to T, and you want to show that S sub n plus T sub n goes to T sub n, goes to S plus T. Okay, so everybody write down what we need to show. What does this mean? That this converges to that. Okay. Just write down the definition. What does that mean? Okay, anybody want to tell me? This should be pretty straightforward, right? You've said it already in this class, right? So it's just plug into this thing over here. Somebody other than Anne want to say it? Kaylin, do you want to try?
Sure.
Yeah.
Given any epsilon neighborhood
Mhm.
P
Any epsilon neighborhood of what?
of S plus T,
Exactly. Any epsilon neighborhood of S plus T.
there exists an N such that if
Mhm.
such that if N is greater than, well, little n is greater than big
Big N,
N,
yeah.
S of N plus T of N
Mhm.
is in this neighborhood epsilon, this epsilon neighborhood S plus T.
Exactly. Right. Exactly. Right. So given any neighborhood of S plus T, then you can find a time past which these guys are in that epsilon neighborhood of S plus T. Okay. Let me write this in just the plain old epsilon way rather than using the neighborhoods. So I'm just going to say, given any epsilon, there exists an n past which, this is in there. In other words, Sn plus Tn minus S plus T is smaller than epsilon. Right? The distance between this and that is smaller than epsilon. Right? So in this case, it's maybe easier to understand if we think about it, because distance in complex numbers is just the modulus of the difference. Okay, so we're trying to show that there's some time past which these guys are close together, right? What do we have? We have that we can make this as close to this as we want. We can make this as close to this as we want, right? So what are we going to do? How close are we going to? Did anybody see how we should do it? Right? We know that. Right? So we know Sn goes to S. Right? In other words, we can make this guy as close to S as we want, right? So how close should we make this to S, and how close we should make the other guy to T to ensure that these things are within epsilon of each other? Anybody see how to do it? Natalie?
Could we just say that they're like, the difference between them is less than like a third epsilon?
Yeah, that'll do. So we know this goes to this. So we know that there is an n1 past which Sn minus S is smaller than epsilon over 3. Right? Similarly, we know Tn goes to T, so there exists an n2 past which Tn minus T is smaller than epsilon over 3. Right? Okay. What do we do next? Right? Past this point, these guys are close to this. Past this point, these guys are close to this. So what if we're past both points? What if we're past n1 and n2? Then both of these things happen, right? So that, that's past the max of them, both Does that help us? Does that give us what we want? If these guys are within epsilon, within a third epsilon of their limits, does that help us get that this guy is within epsilon of its limit? Sure. What's the thing we need to invoke? Anybody see there's something we need to relate this thing to these things, right? What's the relation between this thing and these guys here? Let me rewrite this. Somebody whispered it? No?
Is it a triangle?
It is a triangle inequality, yes, right? Because this thing here is the same thing as Sn minus S plus Tn minus T, right? Sn plus Tn minus S plus T is the same thing as Sn minus S plus Tn minus T, right? But by the triangle inequality, that thing is smaller than Sn minus S plus Tn minus T, right? And now you see how we worked in, right? How we get, this thing is actually controlled by these guys here, right? And those guys are each smaller than epsilon over 3, so their sum is smaller than epsilon. Right? So this thing is smaller than epsilon for sure. Okay.
Is
Yes.
epsilon over 2 works?
Yeah, epsilon over 2 of course works, because epsilon over 2 plus epsilon over 2 is epsilon. Yeah. But often in analysis, you're overly cautious and you'll say like epsilon over a billion or something.
So technically you can just, because it's like a separate epsilon, so you can just take the, it's like the weight version of original epsilon. So that it is, when you sum, because they are like symmetries. So like epsilon over 2, 3, 4, 5 works.
Sure, sure, yeah, yeah. Yeah, I mean, the fact that even if you wrote like epsilon here, and you wrote epsilon here, and you got that this thing is smaller than epsilon, smaller than 2 epsilon, you know, it basically does it for you, because you just take, you know, whatever epsilon you're given, you take this as a different epsilon, which is half of that
Yeah,
epsilon,
yeah.
right? So. Doesn't all matter. Okay, is that clear for everybody? Okay, so there's two things going on here. One is just understanding the definitions, right? And then the other is seeing the connection between what you want to control and what you have control over. Right? That's really the key part, right? Seeing you like I'm trying to get control over this thing. I have control over this thing. Well, how does the control over these guys give me control over this thing? Well, triangle inequality is the thing. Okay. Can you imagine? Well, okay. So let's do number 2. I'm not sure if I want to do number 2. I'm not going to do number 2. Okay. I'll let you. I think try to do number 2 on your own. It's like similar reasoning. Okay. Instead, let's do number 3, which is a little bit trickier. Okay. So number 3, we're given that Sn converges to S, Tn converges to T, right? And you want to show that Sn Tn converges to St, right? So again, you want to show that given i.e. given any epsilon greater than 0, right? There exists a time past which Sn Tn minus St is smaller than epsilon. Okay. So now this one is a little bit trickier. The process of getting from here to there, getting control over this thing, given control over these guys, right? So what we have is we can make these things small, right? We can make these things small, right? But how do we use those things to get control over this thing here? Do you see? Does anybody have an idea of how you might sort of use these things to control that thing? This one, you might not be able to just like come up with it instantaneously. But if you think about it for a while, one thing you might think is like, well, maybe I can sort of like slide in some terms, right? Like if I have Sn Tn, right? I have Sn Tn. If I subtract off an S times Tn, right? Then I can factor out the T and I'll get an Sn minus S, right? So if I like just put that in there, of course I can't just put it in. I have to take it out as well, right? But maybe I can do something like that, right? Yeah, so that's one thing you might do. Actually, I think this is. Let me think for a second. So this would give us Sn minus S times Tn. Yeah, actually, this might not be the right way to go. Sorry. Sorry. Here's a different way. So think like this. So if this is a box, and this is S, these are all complex numbers, but just pretend with me that these are real numbers for the moment. Okay. So pretend like this is Sn, this is S, and this is Sn, this is T, and this is T sub n. Okay. Right. And I'm trying to look at SNTN, which is the area of this box. And I'm subtracting off ST, which is the area of this box. Okay. So what's left? Well, there's the area of this box, and this box. Right? When I take the area of the big box and subtract the area of the little box, well, I'm left with this shell here. Right? Well, what is that shell? That shell is this length here is Tn minus T. Right? So I've got S times Tn minus T. I also have T times Sn minus S, right? And then I also have Sn minus S times Tn minus T. Right? Sn minus S is this length, Tn minus T is this length. So this is this box right here. Right? Okay. So this is the same thing as this, right? So Sn Tn minus St is actually the same thing as S Tn minus T plus T Sn minus S plus Sn minus S Tn minus T. Is that okay? Right. If you multiply this all out, you'll see that you get the same thing. Okay. Okay. So okay. So now I hope you see why we did this, right? We did this because these are all things that we have control over. Right. Okay. So we're trying to show that we can make this thing small, right? Well, this thing equals this, and this thing is smaller than s Tn minus t plus t Sn minus s plus Sn minus s Tn minus t. Okay, is everybody okay? Yeah, okay, great. Okay, so now this thing here, right, this is s times Tn minus t, right? So this is just a constant times, times this sequence, right? We didn't do it, but in part 2, you have that a constant times the sequence is the same thing as a constant times the limit of the sequence. Converges to the constant times the limit of the sequence. Okay, so what's going to happen to this thing? This is a constant times the sequence. As n goes to infinity, what will happen here? Right, what's the limit? The limit of s times Sn minus t is the same thing as s times the limit of Tn minus t, right, as n goes to infinity. Right? Well, what's the limit of Tn minus t? That's just 0, right? Right. Maybe one way, if you're not convinced by that, this is a limit of a difference. And so we can use part 1, right? And part 1 says that that's going to be the limit of t sub n plus the limit of negative t plus the limit of negative t, right? Well, this is going to be t, that's going to be negative t, and so you get 0. Okay, so by part 1. So that limit is going to be 0. By part 1 and part 2. Okay, right? The limit of this thing is also going to be 0 for the same reasons. Okay, so right, these things are both going to go to 0. The only thing we have to control is this thing here, right? So really, it suffices to show that that this guy this thing converges to 0. Right? Because then we'll have three things that converge to 0. Okay. So right. So that is, we need to see that we can make this smaller than whatever epsilon. So so given epsilon, i.e. that given epsilon greater than 0, we want to show that we want an n past which this thing is smaller than epsilon. Okay. So we do the same sort of thing. We know each of these guys goes to 0, right? So right. Sn minus s goes to 0. Tn minus t goes to 0. So how small do we want to make them to ensure that the product is smaller than epsilon? If we make this guy smaller than something and this guy smaller than something, where the product is epsilon, then we're good, right? Right. So, so we know that we know there exists an n1 such that this thing is smaller than root epsilon. We know there's an n2 such that this thing is smaller than root epsilon. Right. Then past the max of n1 and n2, we know that both of those are true. And so this thing is going to be smaller than root epsilon times root epsilon, which is of course just epsilon. Okay, let me sort of review what we just did. Okay, so we're trying to show that if these guys converge, right, then this guy converges to that, right? So what do we have to show? We have to show that given any epsilon, we can find a time past which this thing is smaller than epsilon. Okay. Now this thing is equal to this thing, right? And this thing is controlled by these things here. Okay. Each of these guys goes to 0, right? Each of these guys goes to 0 by the earlier results, right? So I don't know. Maybe it'll be easier if I say it this way. Each of these guys goes to 0. So we know that there's an ns past which this thing is smaller than epsilon over 3. There's an nt past which this guy is smaller than epsilon over 3. And what we need to show is that there's a time past which this guy is smaller than epsilon over 3. Okay. So, right, this is the only thing that's left, right? So it suffices to show that, sorry, I kind of messed up here. Suffices to show that there exists an nst past which this last term is smaller than epsilon over 3. Okay. Sorry, I think I made things a little bit more confusing than they needed to be. Okay. Well, we know that there's an n1 past which this guy is smaller than root epsilon over 3. We know there's an n2 past which this guy is smaller than root epsilon over 3. So let nst be the max of those two. Then past nst, this thing is smaller than the square root of epsilon over 3 times the square root of epsilon over 3, which is epsilon over 3. Okay. Sorry, I hope it's clearer now. Any questions? Any questions? Long?
No.
Julia? No? Caitlin? No? Okay. Okay. Let's do the last one, which was the reciprocal one. Right? That if you look at the reciprocal, then it converges to 1 over the limit. Okay, so so you want to show that 1 over s of n converges to 1 over s. In other words, that given any epsilon over 0, there is a time such that if you pass that time, then this thing is smaller than epsilon. Right. So I know it's dull to write what you want to do, but I think it's useful. Okay, so let's think for a second. Right, we're trying to get control over this thing, and what we have is, right, what we have is control over this thing, right? We have control over the difference between Sn and S. Right. We have control over the distance between Sn and S. And anybody see how we can work in an Sn minus S into this thing? Right now we've got 1 over Sn minus 1 over S. Does anybody see an Sn minus S in here? And don't say, as my son would, just ignore the top and move this thing down. My son, when I thinks of subtracting negatives, he says, well, you know, the second negative, you just turn it sideways and it becomes positive, right? It's like, I don't know. Yeah. Yeah. Anybody see where Sn minus S actually kind of comes out of here? Yeah.
Could we make the denominators the same and then?
Yeah, so use fractions. Right? So we get S minus Sn over Sn. Right. Of course, the top is the same thing as Sn minus S. Okay, so we're trying to make this thing smaller than epsilon, right? So what? Right? We're trying to make this whole thing smaller than epsilon, and we have control over this top thing, right? So what do you think? Right? How small should we make the top? How small should we make the top? Right? We know that there exists a time past which, right, this is how our argument's going to go. There's a time past which Sn minus S is smaller than something. What do you think we should choose as that something? And I'm completely misleading you, but I'm going to lead you this way anyway. I'm trying to make you guys make an error, actually. I'm trying to force an error here. Okay, I'll make the error. Okay, so like, well, what if we do something like, what if we make this thing smaller than epsilon times the absolute value of SNS? Okay. In that case, you know, then this thing here is going to be smaller than epsilon times SNS over SNS, and then these things cancel and you just get epsilon. Okay, that's what I'm hoping you might say, but it was in order to, so the trouble with that is that you can't do it, right? You can't do that because the n is changing on the right-hand side, right? You can, you have the ability to make this smaller than any constant, right? But you don't have the ability to make it change as time goes, as n changes, right? Because then the n is going to change, right? Then the constant is changing on the right-hand side, and then your n would have to change with it, right? So you can't do this. Okay. So yeah, so that's not what you want to do. Okay. So yeah, that won't work. But it's kind of the right idea. It's kind of the right idea, and the way you get around that problem is the following. You say, well, look, S sub n actually is converging to S, right? So here we try to fix things up. You say, well, look, S of n actually is converging to S, right? So we can actually choose n big enough that S of n in magnitude is bigger than half of S's magnitude. Right? If you're thinking about real numbers, like say, here is S and here is 0. We know that S of n is converging to S, right? So there's going to be a time past which it's more than half of the magnitude, right? Or these are actually complex numbers. Here's S, right? We know that there's got to be some time past which, so here's this length here is the magnitude of S. We know that since S of n converge to S, there's got to be some time past which they're in this ball here, and so the S of n's magnitude is bigger than half of the magnitude of S. Okay, right. You can make them, and you can show this using the triangle inequality as well. Okay. Okay. Yeah. Okay. So okay. So we can actually choose a time past which this thing on the bottom is bigger than 1/2 S, right? So past that n, 1 over SNS is actually smaller than 1 over 1/2 S squared. Okay. This thing is bigger than that, so the reciprocal is smaller than the reciprocal of that. Okay. Okay. So that's, and you see why that's good, right? Why is that good? Why is that good? It's a constant, right? So now we know there's so let's call this guy n1. There's an n2 past which this guy is smaller than, what should I choose here? You want to try, Charlotte? You look like you're thinking about it. Right.
I'm not sure enough.
Right. Right. This thing is going to be smaller than this thing, and then we need something on the top here that will give us epsilon here, right? So what should we put on the top? Right. We'll put epsilon times this thing, right? And then they'll cancel off like we did so speciously before, right? So we know that there's, choose n2 past which this thing is smaller than this, right? Then, if we're past both of them, then the top is smaller than this, and the bottom, the reciprocal is smaller than this reciprocal, right? And so we get that this thing is smaller than epsilon. Okay, and that's what we wanted, right? We wanted an n past which this thing was smaller than epsilon, and we noted that this thing is equal to this thing is equal to this thing, and we found a time past which this thing is smaller than epsilon. Okay. Everybody close your eyes for a second. Am I going, raise a finger if I'm going too fast. Raise a finger if I'm going too slow. Okay, open your eyes. It's okay. Okay, that's it for today then. We're done.